Welcome to section 1.4, a library of functions. This section should be review. I'm sure you've seen most, if not all of it before, but again, we're going to be working on making sure that you really understand things. Now, also, when we introduce certain topics, I'm going to be giving you some formal definitions. The more practice you have learning to read formal definitions, the better off you're going to be later on in math. They may be confusing in the beginning, but I promise you that I will always explain them. All right, so starting off with the most basic type of functions we have, which are linear functions. If m and b are real numbers, m you should recognize as your slope, b is your y-intercept. The function f of x is equal to mx plus b is a linear function. It's in slope-intercept form. If m is 0, if our slope is 0, then we have just this because 0 times x makes the x go away, and it is called the constant function, and it is flat. It is a horizontal line. If our slope is 1 and our y-intercept is 0, which is specifically this case, when you plug in 0 for b, you get this function. This is called the identity function. So identity function looks like this. It basically bisects quadrants 1 and 3. If your slope is 0, you have a horizontal line. If your slope is positive, then your graph is going to be going up when you look at it from left to right. And if your slope is negative, your graph is going to be going down when you look at it from left to right. Now, I know this feels very basic, but this becomes incredibly important in calculus. We're going to be using the idea of slope and all of this stuff over and over and over and over again. So let's just work a simple problem involving a linear function. A tooth from a megatooth shark measures 16.4 centimeters. Calculate the length of a megatooth shark from which it came by using the formula shark length is equal to 0.96 times the height of the tooth minus 0.22. And the shark length is in meters and the tooth height is in centimeters. So this is in centimeters, which means we don't have to do a unit conversion, which is always nice. So all we're really going to need to do is to take this value and plug it in right here so that the shark length is equal to 0.96 times 16.4 minus 0.22. Now enter this into your calculator. And 0.96 times 16.4 minus 0.22 is equal to 15.524. And the length is in meters, so meters. That's all you have to do. That's probably second nature to you at this point in your mathematical careers. Okay, so we were talking about graphs going up or down based on slope. We take this general concept and apply it to things other than linear functions. So we talk about whether something is increasing or decreasing or constant on a particular interval. Okay? If I were to show you a picture of a graph, chances are that all of you could point to those individual areas where the graph is going up, where it's going down, or where it's remaining the same. The tricky part in these problems is being able to write down in math where those things are happening. Let's look at the formal definition first. Okay, if we have a function and we have an open interval, so a function, let's just draw a squiggle here, and I have an open interval like this. Okay, where these are a and b, and a can be regular numbers or they can be infinities, but just an open interval, okay? The graph is increasing on this area if this is x1 and this is x2 and this value is higher up than that one. It's decreasing if you have x1 and x2 in order, but x1 is higher, or f of x1, your y value is higher than your x2, it's going down. And if they are equal, then they are a constant function. That should be bold too. I will fix that before I upload this for you guys. Okay, now alternately, the function is increasing if the average rate of change, which if you recall from the last section, is very closely related to slope. It is increasing if the average rate of change is positive, just like if your slope is positive, your line is going up. And if your function is decreasing if the average rate of change is negative, just like a negative slope means that your linear function is going down. It is decreasing. Okay, now one more concept before we start working some example problems. We have the idea of a relative maximum or relative minimum. Okay, we say in just plain English, if a point is higher than anything else in its immediate area, it's a relative maximum. If it is lower than anything else in its general area, it is a relative minimum. Now, I just said that in plain English. I need to be a little bit more specific, because I said that the relative maximum has to be larger than everything else, but technically it can be equal to as well. So if a point is higher than or equal to everything else in its general vicinity, it is a relative maximum. Similarly here, if the point is lower than every other point in its immediate vicinity, or if it's equal to every point in its immediate vicinity, then it is a relative minimum. Okay? And just one more definition here. Points on a graph where a function changes direction from increasing to decreasing, or vice versa, these are called turning points. Okay, so if we're going from increasing to constant, not a turning point. If constant is involved anywhere in there, it's not a turning point. Just if it changes from increasing to decreasing or decreasing to increasing, it's a turning point. Okay, so let's look at some example problems. I'm going to give you a graph, and then we're going to determine the intervals on which the function is increasing, decreasing, or constant. And then we're going to talk about any local relative maxima or minima, that's the plural for maximum, and that's the plural for minimum, and state whether each is a turning point. Okay, so increasing, decreasing, or constant. Okay, so where is that happening? If I'm just going to draw a picture, if I'm just going to point to the picture, my graph is going up here, and it's going up right here. So those are the areas where it's increasing. We're always looking from left to right when we are determining this. My graph is flat right here, so that is where it's constant. And my graph never goes down, so it is never decreasing. Okay, so how do we write down where that is happening? You're always going to be giving the location based on your x-axis. So if I'm looking for the area where it is constant, for example, I'm wanting to describe this little flat area right here. Well, where is that located on the x-axis? Well, these are marked with 2's. So that is positive 2, and that's negative 2. And that is where my graph is located. So it is constant on the open interval. We do not include endpoints. It is constant on negative 2 to 2. Okay? Because at that point itself, you can't really say whether it's increasing or whether it's constant, because that's where things change. We don't include those endpoints. Now, where is it increasing? It's increasing on two separate areas here. This continues down. The program I'm using to create these graphs does not put arrows on the ends, no matter how much I wish they would. So it's increasing from, where does this go on the x-axis? It continues out forever. So it's increasing from negative infinity up to negative 2 on the x-axis. And then again from 2 to positive infinity. Okay. So that's increasing, decreasing, and constant. Now let's find relative maxima or minima. Okay. So we're looking for the points where a point is either higher than everything else in its immediate vicinity, or the same, or smaller than. Well, right in here, everything is the same, right? So every single point between here and here is either both higher and lower or equal to everything in its immediate vicinity. So in here, we say that the points x, because it doesn't matter what your x value is, 2, that point where x is no matter what it is a relative maximum and a relative minimum on the interval -2 to 2. Okay, everything in here, excluding the endpoints, is both a relative maximum and a relative minimum because it's the same as everything else in its immediate vicinity, and we're allowed to equal to. Okay, so what about these endpoints? Well, this endpoint right here specifically, this point is either higher than everything in its immediate vicinity because it's higher up than anything over here, or equal to everything on this side. So since it's larger than or equal to everything in its immediate vicinity, this is a relative maximum. And by similar reasoning, this point is either lower than everything in its immediate vicinity or equal to. So the point 2, 2 is a relative minimum. Now the last bit is to identify turning points. This graph never changes from increasing to decreasing or the other way around, so there are no turning points.